Kirchoff's laws. This is a German physicist who was able to explain how to solve circuits with two rules. And this is where you're going to really start to see me flog the ski hill analogy. There are two rules. There's one for current and one for voltage. I abbreviate Kirchhoff's current law as KCL. I abbreviate Kirchhoff's voltage law as KVL. Kirchhoff's current law, it comes out of the fact that current is moving charges, moving electrons. Oh, sorry, no. We decided last day we're going to pretend the protons move because it makes the math easier. So current is moving protons, and protons can't vanish. Atoms don't magically destroy themselves or reappear. It's a conservation of charge. Here's what it says. I'm going to give you the English version. I'm going to actually write an equation. I deliberately did not put this on the formula sheet. And then I'm going to show you. And you're going to go, oh, makes sense. The English version says, at a junction between wires, the current flow splits or combines and continues to flow downhill from positive to negative. When a current splits or combines, no charge is lost. The total flow into the junction equals the total flow out of the junction. If I wanted to write that algebraically, I would say this. The sum of all the current in has to equal the sum of all the current out. And you can write that down, but nobody remembers that. We just remember how to use Kirchhoff's current law. Here's what Kirchhoff's current law says. I've told you that current is like skiers. So if I have 2 amps moving in this way and I have 1 amp moving in this way, how many amps come flowing out of that junction? That's Kirchhoff's current law. And it's not going to get much tougher than that. When I'm solving circuits, the first thing I always try and do, if I can, is find any missing currents. In fact, one of the phrases you're going to hear me say, Ange, is if I can find the total current leaving the battery, the question's going to fall apart. I know that already. So, example 1 says, find the unknown currents. First thing I always do, and this is a good habit to get into. You know, Sarah, I'm big on having you write down no-brainer stuff to feel better. I label downhill. Here's my battery. Which is the positive part of the battery, the top part or the bottom part? So downhill current is this way, that way, that way, that way, that way. By the way, which way do the electrons flow? In the opposite direction. That's what's really happening, but we've decided it's going to be much nicer mathematically to think of positives flowing downhill. How many amps right here? 1.75. How many amps right here? 1.75 amps. How many amps right here? How many amps right here? How many amps right here? 1.75. How many amps right here? How many amps over here? 1.75. Current splits up and rejoins, but it doesn't magically create itself or vanish. Let's do one with some junctions. First thing I would do again is I would carefully label downhill, 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 downhill. Oh, on the right at the bottom, what's the correct direction of the current? Pointing to the left or pointing to the right? What's the correct direction of the current on the left on the bottom? Pointing to the left or pointing to the right? Okay. I typically start at the battery and I start following the current. And if I can find total current, this question's going to fall apart. How many amps are leaving the battery? I'm not sure. Oh, yes, I am. How many amps right there? How many amps right here?
3.
Now let's follow it. How many amps right here?
3.
How many amps went this way?
0.8.
How many amps must have gone that way? 2.2. Let's keep following this branch. So 2.2 amps, 2.2 amps. How many amps are going through this resistor then, for what it's worth? 2.2 amps. If you stuck an amp meter in that resistor, that's what it would read. How many amps right here?
2.2.
How many amps right here? Because the 0.8 and the 2.2 have recombined 3 amps. Okay. All I can do now really is give you more junctions, or, well, I can make it trickier but not tougher. I'll show you what I mean. Next question. Example 2 says, show the direction of each current and find the unknown currents. How am I going to show the direction? I'm labeling downhill. Downhill is this way, this way. Here it splits up. Some go down, some go to the right. Here it splits up. Some go down, some go to the right. If I follow the far branch around, I guess along the bottom row, the current is flowing to the left. Yes? That little bit is worth doing. You feel better, you've written something out, but it really cuts down on mistakes. If I can find the total current, this question's going to fall apart. If I can find the current that's leaving the battery, this question's going to fall apart. Do I know the current that's leaving the battery? Do I? How can I figure it out, Braden? Okay, right here, we've split up into a 5 going that way and an 8 going that way. So how many amps must have been flowing in? How many amps must be right there? How many amps must be right here? How many amps must be leaving the battery? The total current flowing through this circuit is 13 amps. By the way, that also then allows you to calculate how long this battery will last, because current is the number of coulombs per second. If you know how big the battery is, if you know its amp hours rating, you can figure out how long it's going to last. All right, let's follow this small loop. 8 amps went this way. How many amps right here? Not 8. Oh yeah, 13, because I can either go back this way or I guess they recombined. 13 amps. 5 amps went this way. How many amps are in this top right one here? Has to be. How many amps are in the bottom right here? How many amps are in the bottom middle? This is Kirchhoff's rule for current. And again, it's a consequence of, Sarah, protons don't magically vanish. So once you start the protons flow, or on my ski hill analogy, we're not allowed to have skiers go missing. We're not sending out a search and rescue here or anything like that. Skiers don't vanish. Now, my ski hill analogy breaks down because sometimes we'll have currents that are decimals. And what's 1.5 of a skier? Someone really short? No, you know, but we're still going to think of the current as the number of skiers on the hill. Try this one on your own. I'm going to freeze the screen. Let's see if we get the same thing. Label downhill. Downhill along the bottom is to the right. Do I know the total current leaving this battery?
Yes.
Lena? Yeah, I had to go further down, but I see that 5, all the current is going through that resistor, so I can backtrack it to the battery. This question's going to fall apart. Oh yeah, now I got the rest. That's going to be it. Question is, can I fit this on one screen? Yeah, barely. Did you get 3, 2.5, and 5 as the gaps? Okay. Last one here. Downhill is that way. Downhill is that way, that way, that way, that way. How many amps up here on the top? How many amps in this resistor? 3.5? How many amps in this resistor? Caleb? How many amps in this resistor on the right? 3.5. How many amps on the bottom right here? How many amps going through this middle resistor? 1. And how many amps here? So current splits up and rejoins. A good indication, the amount of flow along a particular path, how many amps, it depends on the resistance. So some handy little tricks. You can survive without these, but they're nice shortcuts. And the first one says this: if the resistors are identical, how does the current split up? How does the current split up? equally. This would be 3 amps, 3 amps. I use that shortcut. That's one that's worth having in your back pocket because it's pretty easy to remember and it makes sense. You can actually use ratios to figure out missing currents. I've never bothered using it. I will say this. If I have 6 amps and this one has a small resistance and I2 has a big resistance, what's going to be bigger, current 1 or current 2? And so now what I think is small resistance, nice wide ski run, big resistance, really narrow ski run. Which one's going to have more skiers? Small resistance, I1 is going to be bigger than I2. Which again, Sarah, I think kind of makes sense. If the resistors are simple ratios of each other, we can relate the currents using the same ratios. I almost never do this. I think there might be one really nasty question coming about 3 lessons from now where you have to use this trick. And here's what I mean. How big is the middle resistor? What did I call it? Or how big is the right-hand resistor? Twice as big a resistor. Yeah, it's going to be I over 2, and this is going to be I. Twice as big a resistor, half the current, which means I can be even more specific. If I got 6 amps coming in, how is it going to split up exactly? How can I have a number here and this number be half as big? It's got to be 4 and 2. And I've seen some profs, some teachers teach it this way. You can solve it all by setting up a little cross multiply dealio. It's doable. I just don't think it's as intuitive. I hardly ever pull this out. Instead, we go to the voltage law. The voltage law, Kirchhoff's voltage law, KVL, that basically comes out of a conservation of energy. Now, it is trickier, but if you wrap your brain around that, then you can solve any circuit. Everything I do for the rest is going to make sense. What does the voltage law say? It says that any height that you gain, you have to lose to get back to the bottom of the chairlift. If I have a 12-volt battery, I have to lose 12 volts if I've arrived back at the bottom of the battery. If I have a 120-volt battery, I have to lose 120 volts if I get back to the bottom. So, for example, let's suppose this was a 12-volt battery, and there was 2 resistors in this circuit. If you lose 8 volts going through that resistor, how many volts must you lose going through that bottom resistor? Has to be. The sum of all the voltage gained has to equal the sum of all the voltage loss. If you gain 12, you lose 12. And we usually don't call it a negative voltage. We just say it's a voltage loss, and that lets us always be dealing with nice positive numbers. So, the height of the chairlift, the battery, has to equal the sum of the hills, the voltage drops. Example 4. Supposing we had a voltmeter and we were measuring all sorts of places here. It says find the unknown voltages and voltage drops. This battery gives us a 20-volt gain. So how many volts would we measure right at that location? How high are we still? Now, the wires, we're going to say those are flat trails that lead to the ski hills, so we don't lose any voltage through the wires. In real life, you do lose a tiny bit, Kevin, but that makes the math yucky, so we're going to ignore that. And you know what? We're just going to invest in good wires where you lose almost nothing. So what's my voltage at the top of the hill still? When I go down this hill, how many volts am I losing going through this resistor? Leaving. Now, if I hooked up a voltmeter right here and right there, it would measure 8 volts. And this is why we keep saying voltage is technically a change in. In fact, a voltmeter would measure negative 8 volts because it would say you're losing 8 volts going through that particular resistor. Can you see where it would get the negative 8 from, even though none of those numbers appeared in my little circuit diagram? How many volts do I lose here? I don't know, but I do notice this got me to the bottom. How many volts am I at the bottom? So how many volts am I here? 0. How many volts must I have lost going through that final resistor? Has to be. That's the voltage rule. Let's do another one. Here is a 10-volt battery. Here is a 10-volt battery. So I guess we gain 10 volts, which means when I'm following, I didn't label downhill, and I really should have. I just intuitively followed downhill with my eyes, but that's what I'm doing. And we have to then burn off 10 volts, except, this is important, any legitimate ski run is legal. Here's one ski run, if I ski that. But there's another one. Can do that one. Let's do the blue one. I have 10 volts. How many volts do I still have at the top of this hill? Haven't used any up yet. Whee! I go down the hill. Sound effects are optional. Here, does this get me to the bottom of the chairlift? So once I've gone through the resistor, how many volts high am I right there? So how many volts did I lose going through the resistor? That's the blue run. Could also ski the purple run. How many volts high? 10. How many volts high here still? Whee! I go through the hill. How many volts high am I at the bottom?
0.
So what did I lose? How many volts did I lose in the first resistor? How many volts did I lose in the second resistor? Mr. Duick, are you telling me that a 10-volt battery can run 20 volts of stuff? If you wire it right, yes. Also probably means you'll need twice the current. You'll burn this battery out twice as fast. But nothing wrong with that. This is one that bugs kids, though, because a lot of kids want to say, shouldn't that be 5 and 5? Because it's 10. No, that's a legitimate circuit, 10 volts. That's a legitimate circuit, 10 volts. So another one. Kick it up a little notch. Here we have a 12-volt gain. What batteries are 12 volts? Car battery. Okay, car battery, standard car batteries. I think it's 12.6 or 12. We round off typically. Okay, so this is golf cart batteries are typically 6 volts. How many volts on this battery? You know what? Let's pause for a second, Mr. Dewitt. I didn't do this little speech yet. 12 volts is the car battery. How many volts right here? Someone said 8, someone said 4. We lose 8 going through here, leaving how many? 4 volts? Okay. I should have labeled downhill just so that I could see which way was downhill. This mystery resistor, I don't know, but I do notice I'm now at the bottom. I'm 0 volts there. How many volts right here then? How many volts do I lose, Braden, going through this resistor? By the way, how many volts high am I over here? Also 4. At the bottom, I'm 0. I lose 4 volts here. And again, this bugs kids because they see 8 and 4 and 4. How are you running 16 volts from a 12-volt battery? I'm not. I'm running 2 separate 12-volt subcircuits. And I'm draining the battery faster. What if you have more than one battery? Lesson 7. We'll look at that. Okay. 60 volts. 5 car batteries. Quick look at Bunny. Next time go during lunch. So we have a 60-volt gain. Braden, how many volts would I measure here and here? Each of those would measure 45. Down this middle circuit, I lose 18 volts. Whee! How many volts right here then?
27.
How many volts do I lose in this bottom resistor? I have to, because that got me to the bottom of the chairlift. When you get to the bottom of this battery, bottom of the chairlift, you got to be back to 0 volts. Otherwise, you would have extra energy left over, and that would go into heating up the wires, and that's a bad thing. Oh, this is a bit tricky. Oh, no, wait. I got 45 volts. I lose 10 volts here. I guess that puts me at 35 volts. What's going to go right here? Gotta be. Which means how many volts did I lose going through this particular resistor? By the way, you can imagine that the skiers came to a fork in the path and they split up. Some went to the right, some went down. The ones that went straight down, how many volts did they lose? 18. The ones that went to the right, how many volts did they lose in total? These guys went down one big hill. These guys, you're with me, I'm not as good a skier. I went down a small hill and a small hill. But we each had to lose the same height. Otherwise, how the heck could we meet up at the bottom? If you had gone through 25 volts and I went through 18 volts, we're not meeting up anymore. We're on different altitudes. So you can also use that as a shortcut if you notice that two areas of the circuit split up and rejoin, fancy word, are wired in parallel. They must have the same voltage drop. So there are really two useful conclusions to draw from Kirchhoff's voltage law. For any complete loop, voltage drops equal voltage gains, but also no matter which way you go between points, the voltage drop there and the voltage drop there have to be the same. That's often a nice little shortcut where you don't have to ski the entire ski run. This is a cumbersome notation. In reality, we don't label every single area. We label the battery and we label the resistors. We don't put the top and the bottom, it just clutters up the diagram too much. I've debated removing this. My friend who typed this up, I respect enough to leave this. He said, to see the voltage relationships, it's sometimes helpful at first to redraw the circuit so that everything is pointing downhill. In other words, this circuit right here could be redrawn as big chairlift. Everybody goes down that hill through that resistor right there. We split up. Some people go down that hill, some people go down that hill. That kind of has you always moving downwards. I'm going to say if you feel like you need to redraw them, go ahead. I'm going to push you into just getting comfortable moving your eyes around in the proper direction because it's less time. So 5B could be redrawn as big chairlift. Everyone goes down V1. Some people go down one big hill. Some of us go down two smaller hills. We all meet up and we all go down the final hill together. I don't know, maybe that's a little easier, but it's so much work. I'm going to say, Kevin, let's learn to read these. I'm going to skip example 6. We're going to go to example 7. At the top of this page, I said you didn't need your formula sheet. You don't. Can you write down Ohm's law? Which, if you've done the homework, you probably have memorized. If you haven't, you want to memorize it, even though it's on your sheet. Example 7a says, suppose we have two equal resistors along a path. What can you tell me about these voltages? It all starts with current. How much current is leaving this battery? I'm going to call it I don't know. How many amps are in this top wire then? I amps. How many amps are going through this this resistor? Lena? Loud and proud, you're right. Yep. How many amps are going through this bottom resistor? Also, I amps. What did I write at the top of the page? Loud and proud, what? Do these both have the same current? Does the question tell me they're both the same resistor? Same size? So if I is the same and R is the same, what can you tell me about the voltage drop in each of these? More specific, since I got 30 volts to play with, it's got to be 15 and 15. And I can do that with no numbers. Has to be 15 and 15. Since I and R are identical. What if they're not the same? I'm going to make the same argument, because it all starts with current, that each of these have the same current. I got the nice ones over there too. Okay, you got ones with lotion? They're worth it. So, if I wanted to calculate V1, or by the way, are the resistors the same this time? So, V1 would be I times a big R. V2, same I, times a little r. Which resistor is going to use up more voltage? V1 or V2? Has to be V1. Same I, but bigger R. Okay? V1 is going to be bigger than V2. In fact, we can use that ratio trick again. The same way we managed to get the 4 amps and the 2 amps out of that 6 amps. If they're simple ratios of each other, they're going to split the voltage up in a 2-to-1 ratio, except is this going to be the 2 and is this the 1, or is this the 2 and this the 1? Let's figure it out. They're both going to have the same current. Which is going to give you a bigger answer? I times R or I times 2R? So this is going to be a bigger voltage, and these are in a 2-to-1 ratio. How can you split up 30 volts in a 2-to-1 ratio? I have never used that trick, but I've seen some profs teach nothing but that trick. I mean, there is a way, I guess, you can do it all with cross multiplying, and fine. I just never bothered. Okay. What we are going to use is Ohm's law, which you just wrote on the previous page. And on the top of this page, I'd like you to write Joule's law. And you may notice that there are a total of 4 variables: voltage, current, resistance, and power. If I know 2, I know 4. If I know 2, I know 4. You give me 2, I can find 4. That's the third Kirchhoff's rule trick I'm going to tell you. So I wrote here, although it's helpful to label the voltages at each point, it's desirable at this point now, we're only going to label the gains and the drops. We're not going to label all the wires in between. It gets cluttered. So this says find the unknown voltage, drops, currents, resistances, and I'm going to add one more thing, and powers. First thing I always do is I want to try and find total current. And we'll write this down in an order later on, but I'm telling you, total current. Do I know the total current? Actually, even before that, I should label downhill, Matt. Right? Downhill, 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 downhill. Takes 1 second, and now I know which way I'm moving my eyes. How many amps are leaving the battery? Sorry, how many? How do you know? 4 amps, no junctions in between. The current leaving the battery is the total current. So do I know the total current? This question's going to fall apart. I fill in any other currents that I can. 4 amps. How many amps went this way? How many amps must have gone this way? I filled in all my currents. The second thing I look for is anywhere that I know 2 things. Any resistor that I know 2 things, that I know 4 things. Do I know 2 pieces of information here? How many ohms is that resistor? Look at V equals I times R. In your head, please rewrite it to get the R by itself. Go to your calculator or do it in your head. How many ohms is that resistor? I think 1.5, but double check me. 6 divided by 4, yes? I will not make you show that typing. I am fine if you go, but I will say label whatever you find. So I will, when I mark these, you'll see I would give 1 mark if I saw that. How many watts of power is this resistor using? What does power equal? V times I, 6 times 4, 24 watts. Yes? Because if I know 2 things, I know 4 things. Is there any other resistor that I know 2 things in? Do I know 2 things here? Say no. Do I know 2 things there? Say no. So step 1, downhill, label that. Step 2, find total current and any other currents. Step 3, if I know anywhere I know 2 things, I know 4 things. Step 4, ski. Ski. Ange, would you come skiing with me? Can I take you skiing, please? Let's go skiing together, okay, Ange? So we're going to start at the chairlift. And Ange, I want you to notice I can go on that run. All of those are downhill always and ending up at the bottom. Sometimes one run will be smarter to do first. I think here it doesn't matter. So we're going to ski this smaller run. How high right now? How many volts? 18, Ange, thank you. How many volts, Ange, do I lose going through that resistor? Leaving? 18 take away 6. Yeah, leaving 12. Ready, 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 ready. Whee! Went down that hill, you and I. You're a good skier. Did that get us all the way to the bottom? How many volts must I have lost going through that middle resistor then? Yes. Ange, knock, knock. Do I know 2 things? I know 4 things. See it? How many ohms is this resistor? 4? Yes? How many watts of power is that resistor using? 36? Thank you for skiing with me, Ange. Sarah, want to go skiing with me? Let's go skiing. Sarah, you and I, we're going to do the outside one because it's longer. So you ready? Here we go, here we go, here we go. How many volts am I starting out with? 18? Whee! How many volts did I lose going through that hill, that resistor? Leaving how many? Whee! Thanks for coming down that hill with me. Did that get us to the bottom? Sorry, I'm trying to look well. Did that get us to the bottom? So how many volts must I have lost going through there? Sarah, knock, knock. I know 2 things. How many ohms are, I think, is V over I? Is that correct? Looking at the equation. In your head, 12 divided by 1, no calculator. 12 ohms. And power is V times I, 12 times 1. In your head. So, by the way, this is too easy a question, but isn't it 12, right? Did I make a mistake? I'm good. Sarah, this is too easy a question, but here would be a good test question. Supposing I said, these are all light bulbs. Which of these bulbs is the brightest bulb? My mom says I'm not the brightest bulb. Caleb, she means something different. Which of these is the brightest bulb? Which of these is using the most power? 36, right?
Yes.
Which of these is the dimmest bulb? My mom says I am the... No, Caleb, she means something different.
The one on the right.
The 12.
Yes.
Okay. Light bulb questions are great ways to have you analyze a circuit. And power is brightness. B. Thank you for skiing with me, Sarah. Label downhill. By the way, in the questions, I didn't ask you to find R or P, but I'm pointing out to you, Kieran, I can. So in our notes, I will, and then in the homework, find whatever they want you to find. But if I know 2 things, I know 4 things. I want to, if I can, now that I've labeled downhill, find total current. That's step 2. Do I know the total current leaving the battery? I do, sorta. What does the total current leaving the battery have to be? Got to be 2.5, right? Right? Okay? Which means in this first resistor, it's 2.5 amps. Are there any other missing currents anywhere? No. But do I know the current leaving the battery? Kyle, this question's going to fall apart. Kyle, knock, knock. Knock, knock. I know two things. Okay? So I can certainly figure out R and P. R is going to be 21 divided by 2.5. 21 divided by 2. Ooh, boy. Dividing by 2. Well, dividing by 25, same as times by 4 divided by 8.4. Double check me. Yeah. Power is going to be V times I. 21 times 2.5. 21 times 2 is 42. And then a half of that would be another 10.5. So it's going to be 42. Is it 52.5? 52.5 watt?
Watts.
Is there anywhere else where I know two things, Kyle? No. Final step, ski. Kyle, would you like to come skiing with me, please? Okay. Let's try this run first. How many volts have I lost? Leaving how many? Whee! How many volts must I lose in that resistor? Gotta be. Has to be. Must be. Knock, knock. I know two things. I think R is going to be 14 divided by 1, which is 14 ohms. And I think power is going to be 14 times 1, which is 14 watts. How many volts is the right-hand resistor using? Kyle, what did you say? I love the fact that you said this, because there's two ways I can do this. I could do the full ski run again, or I could notice, you know what, since we split up and meet up, this path and this path has to be the same drop in voltage, the same drop in height. So if you're looking for a shortcut, you could say, hey, that's 14 volts. R is going to be 14 divided by 1.5. Ooh, that's going to be a bit yucky. It's going to be the same as 140 over 15 divided by 5 is going to be, oh boy, 14 divided by 1.5. What do you get? 9.3 repeating? And power, that I can do in my head. It's going to be 14 times 1.5. 21, yes? Is it? If those were light bulbs, which of those bulbs is the brightest bulb?
It's the first one.
The 21 volt. Okay. Other questions I might ask would be something like, if I pulled this bulb out, would this bulb become brighter, dimmer, or stay the same? We'll talk more about that later. And no, it won't stay the same. No. Oh, cool. Here we go. Downhill. Total current. Do I know total current? Really? How many amps are leaving the 40? Can't be one, because some had to go this way. I know it's more than one. So do I know total current? Okay. Do I know two things anywhere? Well, then I know three things. This looks like it's going to be 35 ohms and 35 watts. Do I know two things anywhere else? Final step, Braden, to ski. Let's ski. What? On the left side, sorry, on the top or on the right? What are we talking about? On the right here? What do you tell me? Let's ski. Start here. Braden, look up. How many volts? How many volts does this one have to be then?
You got 5.
Got to be 5.
Good math.
Which wouldn't tell me two things, but if I now ski the outside run, this has to be 35, or you could get it by using the shortcut of recognizing these two are in parallel. They're going to be 35 apiece. Knock, knock. I know two things. What's the current here? 7? Yes? And what's the power there? 7 times 35. That's going to be 210 plus 35. 245? Which, by the way, suggests to me that's not a light bulb. That's probably some small appliance, because generally light bulbs don't get much bigger than 120. I think the heat lamps that you sometimes see in barns and things like that for, keeping chickens and things warm, I think those are about 150 watts. We don't go much higher than that. You can. Hey, how many amps are going through this resistor up here? How many? 8. Because I got a 1 and I got a 7. Matt, do I know two things?
Yep.
Then I know everything. Resistance is going to be 5 divided by 8, which is 0.625. And power is going to be 5 times 8, which is 40 watts. Little piece of advice, by the way, always put units on here. Otherwise, you'll look at these numbers later on and forget what's what or what's what. Yes?
The 7 amp shouldn't be a decimal because you're dividing the 5 by the 35.
You're not dividing the 5 by the 35. You're dividing the 35 by the 5. Because I'm pretty sure if you go V equals I times R and you get the I by itself, it's V over R, not R over V. And by the way, people do that, and I'm sorry, dumb mistake all the time. They do the math in their head and they accidentally have reciprocaled the wrong way. Don't do that is all I can say. A couple more, we're done. Light bulb questions and then we're good, right? Yep, cool. I may have said this already. I really find solving circuits almost addictive, like the little Sudoku puzzles. This is the same gentle mental joy that I get if you give me a big tangled up string and say untie the knot, untangle the knot. It's something I can just whittle away at step by step, and then suddenly about 3 steps from the end I can see it all coming together. This one here, there's a bit of a typo. This line right here should be right there. Okay? Did you already make it going down?
Yeah.
Okay, then we'll leave it like that then. It won't change anything. Okay, we'll do it that way. It's a glitchy graphic that I haven't figured out how to fix. Okay. How am I going to start? First of all, I don't see currents anywhere. Oh, wait a minute. I can figure out the current there. And even better, is that going to be the total current leaving the battery? This question is going to fall apart. I'm telling you that right now. Is the total current 4 amps?
Yes.
Okay. If they had asked for the power, it would be 32 watts going through that resistor, but they didn't. Did I skip D? I skipped D for some reason, didn't I?
Yeah.
We'll come back to D. Can I say 4 amps went here? No, it's split up. Do I know 2 things anywhere else? Let's ski.
Yeah.
Now, I notice on here there are 2 or at least 1 voltage that I don't know. I might save that for last. I might try skiing the inner run first because I suspect it'll be a little cleaner. So, how many volts does this 10 ohm resistor here have to be? Did I go too fast? How many volts am I gaining? 32. What do I lose here? 8, leaving. Does that get me to the bottom? I have to lose. Oh, and I guess the current is 2.4 amps, and the power is going to be 24 times 2.4. Well, that's going to be 48 plus 9.6 is going to be 57.6. How big does this V have to be here?
It has to.
What? It has to be 14, doesn't it? Because if this is 24, this has to add to 24. Or you could get there by skiing all the way around. We've got a lot of tools at our disposal. It's got to be 14 volts. How many amps are going through this right-hand path? How many amps coming in? How many amps coming in?
4.
How many amps went this way?
2.4.
How many amps went this way?
1.6.
Yep. Do I know two things? I can find everything. So in the bottom, it's going to be 14 divided by 1.6. No idea. 8.75 ohms. And in the top, it's going to be 10 divided by 1.6. That I might be able to do. Same as 100 over 16, which would be 50 over 8, which would be 25 over 4. 5.25? No. 6.25. 6.25. Could I find the power usage in either of those as well?
Yes.
And you'll also notice we're using V times I a lot. Often to find power, you'll use I squared R because I'm teaching you to always find current first before we find voltage. And if the question says find power and quit, you can quit there. The one I almost never use is that one because I will have found current and voltage long before I need to pull that one out. Light bulb questions are a good test of understanding of Kirchhoff's laws. Oh, I didn't do D? I'm going to skip D. When we're talking about brightness, brightness is power. It's related to how many watts. So in this circuit, which bulb is brighter? All I've told you is that R is the same for both. You said they're the same? Convince me. The current's going to be the same? So you ready? I would say this. If you ski this hill, how many volts must I lose there? Has to be. How many volts do I lose in B? Has to be. Is R the same? It does tell me that these resistors are identical, so I'm going to say RA equals RB and RB equals RA.
Yes.
If V is the same and R is the same, what can you tell me about the current? Same I. So, same V, yes? You could even put in brackets 10 volts. Same R, therefore same I, therefore power equals V times I. What did we say about the voltage? They are the, what did we say about the current? They are the, is the same in both. So yes, Braden, you were right. There's a lovely proof. Very little English. Good algebraic. You could also, Lena, I would have no problems if you just decided to say, you know what, I'm going to let A and B both have a resistance of 20 ohms. I'm going to solve this now, because once you knew the 20 ohms and the 10 volts, you could find the current, you could find the power, and you could prove mathematically they're identical. I'd give you full marks there too. Which bulb is brighter? They're both identical. Pardon me?
I just think so.
Convince me.
They both use the same amount of voltage.
Definitely same current. Yes? The question says same R. Yes? How do I calculate voltage? V equals what times what? So if they have the same I and the same R, you can say they have the same. So I'm going to even go with a therefore. Therefore, same V equals I times R. Therefore, same power equals V times I. Or if I had wanted to as a shortcut, I could have skipped those last two steps. You can write that down. I'll come back to it. Because another way to calculate power, I could have gone, therefore, same power, because power, I think, on your formula sheet is also I squared R. And I could have skipped even mentioning voltage altogether, because if you have the same I and if you have the same R, you have the same power. Kirchhoff's laws. All we're going to do for the next few days is say, what if I give you less information? What else can you figure out? And then we're going to find total current. We're going to ski, knock, knock. Do I know two things? What's your homework? You can try number 1. You can try number 2. You can try number 3. Try number 4. Skip 5. 6 is good. 7 is good. 8 is good. You want to reach the point where most of these take you about 30 seconds or so of thinking. And again, if you want to do it all on your calculator, if you don't actually physically want to write out that, Spencer, just be very careful with your rearranging of the formulas because it's easy to make a dumb mistake. But I've told you I'm okay with you doing all that rearrangement in your head. Great. I will mark these just by the numbers you write down. But anytime you find something, jot it down on that location. Yeah, 10 is good. 11 is good. 12 is good.
Yeah.
I didn't say 9. I skipped 13.
Nice.
14 is good. These are ratio questions. I'm really not a big... I can survive without them, so I'll skip 15 and 16. That may seem like a lot, but actually once you get the hang of this, it's about 10 minutes of blazing through. I skipped 15 and 16.
10 minutes.